Okay, so we're going to do the formula writing worksheet number 1, and we're going to introduce polyatomic ions today. So, first off, grab the back of your periodic table. When you look at the back of the periodic table, you will see two things. The first is polyatomic ions, and the other is the holy sheet. And you'll notice I said the word sheet, S-H-E-E-T. So, there are two things that we're going to use this page for. The first is the polyatomic ions. Polyatomic ions are a group of ions that work together. They're permanently bonded together. They work as one, they treat as one, they act as one. So even though it's made out of multiple ions or multiple atoms, you still treat it as one thing. For example, let's take a look at this one right here, carbonate. Carbonate is one carbon and three oxygens. Even though it's one carbon and three oxygens, you don't treat it as one. You treat it as one group. You don't think of it as three oxygens. Yes, there are three oxygens there, but they work together. I always imagined them as Legos. If I have a bunch of Legos, I can build stuff out of them. But if I take those Legos and I super glue them together, they're permanently stuck together like that. I can still use them, but I have to use them as a group. So if I'm talking about a carbonate, it's a carbon and three oxygens that move around, bond as one, swap them around. You have to treat them as one. And everything on this chart treats like that. Here you've got your positive one ions, your cations. You don't really use hydronium. Mostly the only one we use is ammonium. And you'll see it a good bit. Now with ammonium, because it is a positive charge, we're not ever going to change the name on it. You've got your negative one ones right here. You've got your negative twos, your negative threes, and your negative fours, which there aren't a lot. For example, one of the ones you're going to see the most will be sulfate, SO4. And this whole thing has a negative 2 charge. The negative 2 is the charge. The 4 tells me that there are 4 oxygens, but the negative 2 up to the top tells me that I'm dealing with the charge. And this charge applies to the whole thing. So the 4 only goes with the 0, but the negative 2 goes with the whole group. The other side of the page is the holy sheet. These are atoms that can be more than one charge. For example, a good example of this is iron. Sometimes iron has a positive 2 charge. Sometimes it has a positive 3 charge. You'll notice that almost all of these are transition metals in the middle of the chart. And if you remember, I told you you can't use the periodic table to tell me the charge of an atom if it's a transition metal. Now, for example, if we're dealing with iron, sometimes it's going to be plus 2. Sometimes it's going to have a plus 3 charge. I need to know the name of it. You'll have to say, this is iron 2, in order to figure out the formula for it. Now, when you're coming through some of these, like carbon and chlorine and iodine, nitrogen, phosphorus, you can go ahead and cross those out because the only way to get them to have more than one charge is under special, unique circumstances that you're not going to see in normal everyday life. We're talking like nuclear bombs, center of the earth, kind of weird situations outside of a lab. They just don't happen. Okay, so let's take a look at the worksheet. Barium sulfate. Barium is Ba, and if you look on your periodic table, up at the top of the barium column, it has a plus 2 charge. Sulfate is SO4, and it has a negative 2 charge. Positive 2, negative 2 cancel each other out. I don't have to do any kind of bonding. I just stick them together. So I'm going to have BaSO4 SO4. Okay, so lithium sulfide, that's what we've been doing. Let's come down here to zinc sulfate. Now, I can't look at zinc on the periodic table and know the charge of zinc. But if I look at the back of my periodic table, it says that I have zinc with a +2 charge. Now, zinc is one of the transition metals that always has the same charge. So you'll notice there's no Roman numerals right there. Now, sulfate is SO4, and this whole thing has a -2 charge. +2, -2 charge, cancel each other out, no need to cross over, so I'm just going to stick them together. So it's ZnSO4. Now, let's take a look at iron 3-phosphate. Now, iron is Fe, but iron is one of those that can be more than one charge. So I don't know the charge of it. But if you'll notice in the name, see this little parentheses right here with the Roman numeral? That tells me the charge of it. This tells me this is iron 3. Now, when you look at your charges, you've got 1, 2, 3, 4, and 5. So this is iron 3. So I put my Fe with the +3 charge. Phosphate is PO4, and it's a phosphate and 4 oxygens, but they work together, they act together, they bond together, and they are 1 -3 charge. +3, -3, cancel each other out, no crossing over. So I've got FePO4. Now, let's look at nickel hydroxide. Now, nickel is +2. I know it's a +2 because it's got a Roman numeral 2 right there. Hydroxide, even though it is an ide, is not hydrogen. Hydrogen is hydride. The OX right there, the oxide, hydroxide, tells me that I'm dealing with OH, and it has a -1 charge. +2, -1, they don't cancel out, so I got to cross over. I'm going to take the 2 and put it here, the 1 and put it here, and I end up with NiOH, and I'm going to put my 2 here. But the problem is, does my 2 go with the H, or does it go with the O and the H? It goes with the O and the H, and I represent that it goes with both by using parentheses. This tells me that there's 2 OH groups, not 2 H's. Okay, let's take a look at ammonium chlorate. Ammonium is NH4, and it has a +1. Chlorate is ClO3, but the whole thing has a -1. So +1, -1, they cancel each other out. No need to cross over, just stick them together. So I've got NH4ClO3.